Yeah, thanks. So do you hear me well? Okay, so yeah, this is some work that I've been doing when I was in Liverpool. So it's been some time ago. So it's fairly old work, like a few years. And so at that time, Narges was in Linnaeus in Sweden. And so we jointly designed some technique to do some inference of polymorphic artifacts to ensure information flow properties. So after some time, Narges decided to, I decided to go back to France and started in industry. So now I'm in OCaml Pro in Paris. And Narges decided we couldn't work in the same time zone, so she went to the UK. So that's a very straightforward content or outline of the talk. I'll explore quickly the problem, solutions, evolutions, etc. Nothing really fancy here. So the problem that we want to address is to analyze static information. We want to design a static analysis for information flow control. So in programs, typically information flows in explicitly when you have variable assignments, like in x equals y here. And there are complications because you can have implicit flows, like if you have a guarded assignment to x here, it's guarded with the value of c. And here we say that there's an implicit flow from c to x. Okay, so some people say it's indirect, etc. There's a lot of vocabulary here, but the formalization is usually pretty standard. So we adopt a classical setting to address this problem, and we will, in this talk and in the paper, we actually focus on confidentiality. We classify information, which is the kind of data that's in the variables, and we classify them using security labels. So typically it's public information or secret information. This is usually formalized using a lattice L here with a very straightforward partial order and operation, meet and join. And in this paper and the presentation, we only focus on the two-level lattice because it's already quite complicated otherwise. What we present generalize is also to other more complicated domains, like if you have more labels, etc. But that would require few adaptations. So information flow in low-level object-oriented programs is even more complicated to analyze because, like typically here you have a Java program. It's allocating a few stuff on the heap. The heap may have an infinitely many amount of objects, and you have to track aliasing, etc. For the presentation, we have a special output. It's like a toy output statement that just takes a reference, and we say that it outputs to a public channel, so to the public, any information that might be reachable in the heap from the reference. It's also low level because we have no high level control flow. Here we only have guarded branching statements. Okay, so goto and labels only. This is to match what we can find if you take Java bytecode directly, and so it's just to make the problem more interesting. There are many approaches to analyzing information flow and to perform information flow control. Here I mostly cite the sound approaches. There are many unsound approaches. Okay, so you have many stuff like type systems. You have abstract interpretation based approaches. You have other approaches like self-composition that take the program, duplicate it a bit, merge them, and then you can check satisfiability. Yeah, you can check some kind of safety property that ensures non-interference. You have other approaches like theorem proving. Most common weaknesses of these approaches is that the heap abstractions they are using is typically very imprecise, and they sometimes ignore completely implicit flows, okay, or they impose harsh constraints on what can happen in a high context. High context is when after you have passed a branch on a high sensitive condition, a condition that depends on a secret. So what we want to do here, as I said in the title slide, is we want to infer polymorphic information flow guards for the methods of a full application given as a bytecode. Okay, so low level. We want the guards to be polymorphic so that they can apply in any calling context. Whenever we see a call to a method, we have a guard or an artifact that's polymorphic, so we can reuse it immediately. So that's one of the points of having polymorphic guards. And this allows us to implement a bottom-up approach. So when we have a method to analyze, we can encode the security semantics of M, which is a way of modeling how information flows between the variables and the objects, etc. We use it. We do this by generating a symbolic transition system, and then when we encounter a call to a method, we can reuse the guards we have already computed for this method, for the called method, to construct the symbolic transition system S. And then we do some kind of analysis of S to compute a guard. Okay, I will detail that in the next slides. Okay, so one side effect of this is, one beneficial effect is that each method is analyzed only once. Okay, also it parallelizes well, etc. So yeah, there's a side case where you have potential recursion, in which case you need to loop and you have some kind of overall fixed point, but we'll put that aside for now. So let's see a first example. It's quite straightforward. We have two classes, A and B, and a static method that takes a few arguments. We allocate an object of type B, we put its reference in R, etc. So we have a local variable here, local reference variable. We do a few modifications of its fields, and we output the contents of B at the end to a public channel. So generating the symbolic transition system is rather straightforward, actually. We have locations here, square boxes, so discrete locations that all mostly correspond to a statement in the method. We have transitions that are guarded, so the guard is before the comma on the label of the transition. And after the comma, we have a set of variable assignments. We have a symbolic transition system, so we have locations and we have state variables. So here R with a bar on top describes actually the security level. Okay, so the classification of the information held within the local variable R. Okay, as we have this is the implementation of a typical encoding of the information flow for programs. As we have just assigned R, we say that we set its level to that of PC. PC is a special variable that holds the security level of the calling context, okay, which is the level that of every information that was accumulated over guards before M was called. We have a notation that we will expand later about heap manipulations. Okay, so this is a way of abstracting what we do about heap objects, and etc. Here we have a very straightforward structure for the symbolic transition system. The transition systems we generate are always deterministic, so we can always, so there's no ambiguity on the transitions we take. And they are reactive, so there's always at least a transition whose guard is valid. Okay, so as I said, we have state variables associated with those symbolic transition systems. Here we have only security level variables. Okay, they describe what we use to encode the information flows in this method. We have, so as I said, the security levels for the execution context, the local variables, or I mean the formal argument and the local variables distinctly, whether they are primitive variables or reference variables, doesn't matter here. It's just the same. And we have, for now, notations to encode the security level of every object that is reachable from any of the reference variables. Okay, so with the little arrow here means that from A I can reach a set of objects, okay, from the reference A, and the security level held here by any of those objects is you can have an upper bound held in the value of A, a row of this variable here. So to explain a bit more this example, we can replace each of these notations here dedicated to the heap with actual variable assignments. So let's say R, we encode it with a variable which holds security level. Okay. This transition, this assignment here gives us this actual assignment. Okay. And what we have here in the notation that I forgot to mention is a way to express the level of the information flow that goes to the heap when we perform some mutations. Okay. And here, so here we have the context when the security level of the context when we allocate the object. Here we perform, on the second statement, we perform a mutation. So the security level that flows to the object modified here, A, is the upper bound between the level of I and the current execution context. Okay, so we can do that for all of those notations here. Yep.
Is PC a variable or
It's a symbolic variable here. It's just yeah, it's a variable. It's a special variable. I think PC is a standard notation in I think it's what's called language security. I think. Yeah, it stands for program counter indeed. Maybe I should have added a bar on top to make it more clear. So we expand that, and in the end, we have an output of information. And what we want is to express a safety property that any information given to output is public. Okay? So this can be expressed here, like we map the location L3 that corresponds to the output with some kind of formula here that expresses that the output happens in a low context and that any information given, be it the reference itself or the objects reachable via the reference, are low sensitive. Then what's missing here is also the initialization, and the initialization is just a predicate that expresses constraints on the what's local to the method. Okay, so here it's only R. Note that it's only the local variables. Everything else, which is actually related to the calling context of the method, so everything about the arguments and the execution context, is left uninitialized. So to explain, to like exemplify a bit more the semantics of this, we can start with a tiny execution. We have I here. We say that the information given to this formal argument I is secret. Okay, so it's high level. And if we apply, we move from L0 to L1. We apply this. We can do this because it's only its guard is always holds, like every guard in this symbolic system. And we can apply every assignment. Every assignment is applied in parallel. It's just a detail. And we move to a new valuation for the state variable. So the state here is the pair between a location and an assignment for all the variables. And if we continue, here we have raised the value for the security level for every object because we don't know anything about aliasing. Here we could have an alias. So what's happening? Here we have to raise the level of I because we are assigning to the object. We are actually putting secret information in the field of A, but actually B, as we can see, can have a field that references an object of type A. So A can also be can also be referenced or reachable in the heap via B. So we have to raise the level of B, etc. So here we find that we can violate the confidentiality property. So now, given this kind of symbolic system, we can actually compute a guard for the method via a very straightforward or standard weakest precondition problem. So we have the symbolic system and we have the safety property. We can backpropagate the safety property back to the initial location and obtain a precondition for the method. And this precondition is actually the guard. So if we do that, I will go a bit fast, but we apply a straightforward fixed point to this method. This terminates here because we assume the level. So every variable here is of finite domain. So we can assume, we can say that the analysis will always terminate. We backpropagate according to the pre-image the pre-image of each state, and we obtain a guard for the method. Okay. Here it's very restrictive. Like we cannot call the method in a high context, and every of the variable here as argument needs to hold low sensitive information. Otherwise, we might leak information. And the method might not be secure. Okay, so now what if we want to increase precision? We can choose, so there are two ways, and we can just stick to what we've been doing in the previous slides and stick to a propositional logic. This is very straightforward, actually. And we can just continue representing the abstract heap with a finite set of variables. And we obtain the same kind of guards as I've been showing in the previous slide. The other choice would have been to design a full-fledged abstract domain in the abstract interpretation style. But in this case, and we'll see a bit later why it's more complicated, but we would have had a few issues with definitions of some of the operations. I mean, there's a lot of research on abstract interpretation for heap programs, so I don't go into details here much more. So I just wanted to explore a bit more what we could do. So as before, we can keep variables holding security levels, like R a row, and we can add a few variables that hold relations between the references. And using these variables and a few other details, we can refine what we can perform during this co-reachability analysis, the backward weakest precondition computation. Okay, so this set of references actually allows us to define parametric symbolic abstract heaps, because we can just choose any kind of references, of sets of references we want. Okay, here we define 3. We have dump domain, which tracks aliasing, which doesn't track aliasing nor one of the other. It's a deeper style of aliasing that I won't detail. We have shallow that only tracks aliasing, and deep, which tracks both relations. Okay, so dump gave us the guard we had before, and I will just skip here and explain that the guard for dump is just as before. The guard we obtained for shallow analysis allows us to distinguish that B and R actually do not alias each other. And so it's a stronger guard, weaker guard that we obtain. And if we actually add deep, I mean, what we call field aliasing relation, we get an even more precise guard. There is a bit of a trick to capture implicit flows that I don't have time to explain, so I will skip to the next part, and sorry, we can discuss that later if you want. Okay, so I will skip that. The main point is that we have to use several heap abstractions altogether to be able to capture implicit flows via the heap. Okay, we can discuss it later. And we actually deal with method calls by assuming that we have the guard as we computed, and an effect, which is actually a description of the possible behaviors of the method. Okay, and encoding a method call boils down to ensuring a safety property which is given by the guard, and the effect actually gives us variable assignments for the outgoing transition. Okay, so we've implemented this in a tool that's called Guardis. The website is Symaris because the tool that actually performs the inference of guards and effects is called Symaris, but it's not the main point of this paper. It's implemented on top of a previous tool that I implemented a lot of some years ago, which is dedicated to controller synthesis and abstract interpretation stuff. But it has a good, easy to use co-reachability analysis core, so that's what I used directly. And the Guardis tool implements various optimizations that you can only do if you really master the full stack of the tool. We actually have performed some precision evaluations using the tool. It's based on the IFSpec benchmark, and as we can see, we have compared each of the domains. Key is one of the best here in the other tools category, but it should be noted that it's also sometimes require user intervention. Okay, so it's a theorem prover based tool, so it sometimes needs annotations, etc. Our tool is completely automated. Okay, For scalability evaluation, we have taken the ABM benchmark. We have 60 applications ranging from quite a lot of lines of Java code that gave us more than 22,000 methods to analyze. We imposed resource limits to analyze this method because the co-reachability analysis is quite expensive. But over those 22,000 methods, only 146 had to be interrupted after 5 minutes and when they occupied too much of the memory. Okay. Obviously, we can observe that. So note that here, 10 to the power of 0 is this line here is shared among all the graphs, corresponds to 1 second to analyze a method. So what we can observe is many, and here in the x-axis, you have the number of unique reference variables in the code of the method. Okay, so we can observe that it scales reasonably well. I will skip that and go to the conclusion. So we have new methods for analyzing and defining information flow guards and inferring them, based on low-level object-oriented programs. It's all given as a tool, and we gave some evaluations. So it's fully automated, doesn't require any user input. It's completely modular, so we could, in theory, do the analysis in parallel when it's possible. And it's also sound, and there's a proof of soundness in the paper. For future works, obviously, we'll need to present how we infer the effects. We can discuss that later if you want. We should consider other programming languages because the abstraction might, other languages might allow us to refine the kind of aliasing relations and heap-related relations we consider, therefore reducing the number of variables in the symbolic system, etc. Obviously, there's the field sensitivity, etc. Changing languages also would allow us to avoid the big problem that references to objects are everywhere in the Java world due to generics, collections, etc. And that makes it hard to simplify the potential relations we can observe. Okay, thanks.
Well, thank you. Okay, so we have a few minutes for questions. Okay.
Thanks for your talk. Because the way that you infer guards involves some WP calculation, so I was wondering how you can handle loops.
Loops in the...
Because you make a weakest precondition computation at some point. So weakest precondition cannot really handle loops because you will need to have some abstraction of the loop. So how do you handle loops in your approach?
So it's all... No, we can... maybe the phrasing of weakest precondition was not that appropriate. Let's say it's only a co-reachability analysis. Okay, so we have a set... Since we have a finite system, we have a set of states that we want to avoid because they do not satisfy the safety property. So we can completely perform a fixed point and backtrack, perform a backward reachability analysis of this representation of the state.
Oh, okay, thanks.
That's also, yeah, maybe it's not exactly weakest precondition.
Well, so you skipped the implicit, the implicit dependency, right? Do you want to talk a few minutes?
Yes.
I just don't understand. For example, if you go to slide number 2, I didn't get why the lower code. If you type 2 and then you hit enter, it will go back to slide
maybe
2.
I don't know.
Yeah. So why is the example at the bottom more difficult than the one at the top? maybe, you know, the one at the top at the high level, you have the scoping information, but here you don't, you only have go-to. Is that why it's more difficult?
You mean handling low-level information?
Yeah.
The low-level aspect is just.
Why is it difficult?
So there are several aspects. The first difficulty is already solved by existing work. I should probably. So it's solved by existing work. It boils down to identifying. I should do that. Control dependence regions, which associate with each. So every work here uses the control dependence region principle, which associates with every branching statement junction point. That is where the two branches merge together before exiting the method. Okay, and that's a typical pattern that we can use. You have a slightly different pattern for loops, but it's very similar. It can similarly be handled. Okay. Then the difficulty comes from taking the level of the information carried by V here and applying it via the branch that is not taken. That's why it's difficult. You have the branch that's taken by the actual program, but you also have not modifying a variable is also an information. So you have to upgrade the level of information for every variable that could have been upgraded where the other branch be taken. So that's why there's a bit of difficulty here.
Okay, thanks a lot. Any last short question?
Yeah, so it looks like that your summaries or what you compute about a particular method will be approximate in terms of potential aliasing relationships among the parameters. So it seems like you've taken a conservative approach. Have you considered trying to make that a little more context sensitive to see, like, at various call sites whether parameters alias or not?
No. Well, there are various versions of context sensitivity. And I don't know. So the real idea was to really completely abstract away the calling context. So the only thing we want to keep here is conditions on aliasing relationships. We could maybe add some more information, like some typing, but the real idea here was just to stick with that because it seemed like it made more sense for, at least for feedback to developers or if you want to analyze a whole application. Yeah, I don't know what other kind of context sensitivity could be added. But yeah, the overall principle was just to really be as abstract as possible.
Just maybe one like concrete example. If you had like these parameters A and B, like in your example, and there were no call sites in the program in which those aliased, but assuming they did alias, you would report a finding. Do you still report a finding in that case? We just attach the guard to the method, and if it's never called with the A and B aliasing, and it's secure because A and B never alias, then we won't report any issue.
Okay.
So, yeah.
Sorry. Okay, so thanks again.
Okay.